So let's talk about something about the acceleration field. How do you measure that in the Eulerian thing? So acceleration field. Okay. So let's say I have the flow moving in this way, and you are at this point x, y, z. Okay. So now I want to measure that acceleration as a function of x, a general acceleration as a function of x, y, z and time. So acceleration measured at that point is nothing but acceleration of the particle that passes through that point, right? And now acceleration of the particle is nothing but the derivative of the velocity of the particle with respect to time. Okay, now velocity of the particle can also be written as the velocity as a function of when the particle is at x, y, z. So I'm just writing the velocity of the particle in terms of velocity vector x, y. So this is nothing but the velocity of the particle when the velocity of the particle is nothing but the velocity at a point occupied by the particle. So I can just write in this way. So now how do I differentiate that? So this means that xp is the x coordinate of the particle, which also depends on time. Yp also depends on time. Zp also depends on time. So this derivative I can just write first with respect to time. So when I do with respect to time first, so that I can just write v bar plus, now with respect to time I need to do, so but xp is a function of time, so I can write first differentiate velocity with respect to x p and then differentiate xp with respect to time. So this is just a chain derivative. And how do you do a chain derivative? Okay, so this is the acceleration at a point x, y, z, t. So this is the time derivative of the velocity with respect to time, and this is called as local acceleration. Okay, and these let's now further study. So dou v bar by dou t. So we have just used the partial derivative concept because it's depending on many variables. So now dou v bar by dou p can be written as dou v bar by dou x, and dxp by dt is nothing but the derivative of the x coordinate with respect to time, that is nothing but u. So if I assume that u, v, w are the components of velocity in x, y, z, so u will be basically dx by dt, v will be dy by dt, and w will be dz by dt. So this will be dou v bar by dou y. So dy by dt is v plus dou v bar by dou z, and it is w dz by dt. So now this is a general acceleration. So now if acceleration, so this is a vector equation. Now acceleration x direction will be dou u, so vx, I mean x of everything, so v, so dou u by dou t plus dou u. So in place of, basically when you have, this is a general vector equation, so when I write in x direction accelerations, I need to replace v x, I need to take x component of the velocity vector dou u by dou t, x component here, x component there, and x component there. So this is the acceleration. Similarly, acceleration in y would be dou v by dou t plus dou v by dou x u plus dou v by dou y v plus dou v by dou z w. Acceleration in z would be dou w by dou t plus u dou, let's write down in the order, always don't change the order, dou w by dou x into u plus dou w by dou y into v plus dou w by dou z into omega. So this is how, so these terms are called local acceleration, or the temporal terms which depends only on time, and these are terms which are coming due to spatial variation of the velocities. So these are called convective terms, or the spatial acceleration terms, the spatial component of the acceleration, and these, so all these are spatial acceleration terms. Okay, so now when you have a steady flow, when the steady flow, something which doesn't change with time, is steady. So your u, v, y are not function of time. Okay, they don't vary function of time. So all these local terms will be all 0. So dou u by dou t, dou v by dou t, and dou w by dou t are all 0. These are all local or temporal time dependent terms. These will be all zeros for steady flow. Okay, and so for the steady flow you'll have only these three terms, the spatial acceleration terms. So this is how you express the acceleration field in terms of velocity fields, velocity components u, v, w. So let's do a problem now. A steady incompressible 2D field is given. A steady incompressible 2D velocity field given as velocity vector is 0.5 plus 0.8 x I plus, so this is given in the Cartesian coordinate, 0.8 y j. Okay, so find the stagnation points. The question is find the stagnation points in the flow field, and the second question is calculate the acceleration at the point 2, 3. So this is the question. The velocity field is given. Now stagnation points, so it means that when something is, when you call a stagnation point when you say that the velocity is 0, I mean all the components are 0, so your ux is 0, or I mean if I assume u, v, w are the components, now it is a 2D field, so you will have only u and v. So when I say the velocity vector is 0, it means u is 0 and v is 0. So both the x component and the y component is 0. So that is the stagnation point. So when I equate these two equations, I get x as minus 0.5 by 0.8, which is nothing but minus 0.625, and y as 1.5 by 0.8, that is 1.875. So this is my stagnation point. Okay, now acceleration. Well, acceleration we have already derived that equation, so let's calculate the acceleration terms. Dou u by dou t plus dou u by dou x u plus dou u by dou y v. Now I'll not use the jet terms because it's only a 2D term, so even if I write this, these terms will be 0, and ay will be dou v by dou t plus dou v by dou x u plus dou v by dou y v plus dou v by dou. So basically you will differentiate with respect to only one component for that acceleration component. So az will not be there, but let's write down a general equation. Okay, so dou u by dou t, the time dependent terms are not there, it's a steady flow thing. Dou u by dou x is basically, if I differentiate this u component with respect to x, I get 0.8, and u is 0.5 plus 0.8 x. Dou u by dou y, I have minus 0.8, and v is the same thing. So this is the component. I don't have w here, w is 0. So this is acceleration of x, and acceleration dou v by dou t, there is no y term. Dou v by dou x, sorry, this is dou u by dou y. So u is basically 0.5 plus 0.8 x. So when you differentiate that with respect to x, you get this, and u is this. Dou u by dou y, you don't have y terms, so this will be 0, and v is that. So this finally comes out to be 0.8 into 0.5 plus 0.8 x. So this is your x component of the acceleration. Dou v by dou I, v is your 1.5 minus 0.8 y. So you don't have anything x derivative, and u is, so this anyhow going to be 0. Dou v by dou I is minus 0.8, v is 1.5 minus 0.8 y, and the other terms are all 0. So this comes out to be minus 0.8, 1.5 minus 0.8 y, and all these terms are 0 for the component. So now at point 2 comma 3, x would be 0.8, 0.5 plus 0.8 into 2, which is 1.6, and this comes out to be 2.1 into 0.8, that is 1.68 meters per second square is the x component of acceleration. Y component, well, you get minus 0.8, 1 minus 0.8 y is 3, so this turns over to minus 2.4, which is minus 0.8, minus 0.8. So this value comes out to be 0.720 meters per second square. So these are the components of acceleration in xy z. Okay, so now let's see some of the flow visualization parameter, and then we'll define two important quantities, the stream function, the velocity potential. So first let's see what are the different flow visualization techniques of flow visualization pattern. So one is your streamlines, then the path lines, okay, and you have streak lines. So most of them are just definitions, but but all these things will all coincide for steady flow. So let's see what is a streamline. So a streamline is a curve